Hello everyone, this is Vani.
Hi everyone, I am Sukanya.
And today we're going to demonstrate our smart temperature sensor.
Welcome to the description of our smart temperature sensor. We'll start from the system level description. As you can see in the system level overview, this is the temperature sensing unit, which is basically a PTAT circuit, and it detects the temperature with its BJT in PNP configuration. The voltage reference circuit produces a low voltage of around 0.6 and it is used to bias the internal amplifier of our circuit. The internal amplifier amplifies the output and produces a range of voltage corresponding to minus 20 degrees Celsius to 50 degrees Celsius, which is the specification mentioned for our design. This voltage is then given as an input to the Arduino Uno board, which is first converted to the digital format by ADC bits and then programmed to corresponding temperature. Finally, the temperature is displayed both on Celsius and Fahrenheit scale on the LCD screen. Next, we're gonna describe one of our critical block, that is the PTAT circuit. As you can see in the figure, this is the error amplifier, and here it maintains equal voltage at node 1 and node 2. Here the current I1 is M times of that of current I2, as the transistors at the top are current mirrors of each other. Since the error amplifier maintains equal voltage at node 1 and 2, we can conclude that VF1 is equal to dVF plus VF2. Here VF1 and VF2 are base emitter voltage of the diodes. Also, we can conclude that I2 is equal to I3 since the output of the amplifier drive the current source and so their gate source voltages are equal. If we apply KCL, we can see that the VPTAT output is amplified version of dVF as explained in all these equations. Hence, the voltage dVF is proportional to absolute temperature and thus VPTAT output is directly proportional to temperature.
Next, we're going to talk about the voltage reference circuit, also known as the band gap reference circuit. The BGR follows similar principle and it works by producing a zero temperature coefficient by cancelling the negative temperature coefficient of VF1, which is nothing but the base emitter voltage of the PNP configured diode, and the positive temperature coefficient produced by dVF. So, in a sense, BGR is equal to a PTAT circuit with an additional complementary to absolute temperature circuit, thus providing an output voltage which is invariant of process, voltage and temperature variations.
Here the temperature chamber shows a temperature of 23.1 degrees Celsius, and we can see the LCD screen that in Celsius it shows a temperature of around 25.7 right now, and it keeps on fluctuating because we are getting an accuracy of plus minus 2 degrees Celsius.
As you can see, now the temperature of the temperature chamber is set at 45.3 degrees Celsius. When we note at the multimeter output voltage of the PTAT circuit, it's around 0.894 volts. And when we measure the temperature based out of the Arduino, it gives you 46 degrees Celsius. As you have observed from the previous note, when the temperature of the chamber was set at 23 degrees Celsius, there's a temperature variation of plus or minus 2 degrees Celsius. The same can be observed in this reading also. We decrease the temperature of the chamber to minus 15.1 degrees Celsius, and based on how a PTAT should work, the output of the multimeter output voltage must also decrease. And as you can see, the same thing happens over here. As the temperature increases, the output of the VPTAT increases, and as the temperature decreases, the output voltage of the PTAT circuit also decreases correspondingly. Now, when we see the temperature measured by the Arduino, it shows around minus 12 degrees Celsius to minus 11 degrees Celsius. This shows that the accuracy would decrease to plus or minus 3 degrees Celsius as the temperature goes below 0 degrees Celsius.
This is the measurement setup of voltage reference circuit whose output should be constant across process, temperature and supply. At this point we can see that at 23 degrees Celsius we are getting a voltage of 0.632. At the same time we are also analyzing error amplifier whose function is to maintain equal voltage at its two nodes. We can see that at its two nodes we are getting around 0.82 voltage. The next temperature we are measuring it is at around 50 degrees Celsius, where the voltage reference is around 0.634 volt. Here we are getting an offset of 2 millivolt, which is acceptable for our application. The error amplifier shows equal voltage across its two nodes.
We have now set the temperature of the temperature chamber at minus 20 degrees Celsius, and the measured band gap reference voltage at this temperature is 0.63 volts. We measure the voltage of the error amplifier at this temperature. The input voltages are almost the same. So this explains that the accuracy of our BGR circuit is plus or minus 2 volts, with 0.632 volts as the output voltage at the room temperature, and our error amplifier maintains same voltages at both its inputs at all temperatures varying from minus 20 to 50 Celsius. Now demonstrating our temperature sensor. This is our chip. The chip is powered using a 9 voltage power supply over here, which is first passed through a voltage regulator which converts it into 5 volts, and then we use another voltage regulator to convert it into 1.2 volts, which is required for our chip to operate. We are measuring two outputs from our chip. One is the band gap reference output and the other one is the PTAT output, which gives us a temperature and a voltage correlation. You can see that we are measuring both the outputs at room temperature over here. This is the band gap reference output. That means our chip is going to produce a constant 0.63 volts throughout a temperature range of minus 20 to 50 degrees Celsius, and this is the PTAT output voltage at the room temperature. We are then feeding the PTAT output voltage from this pin into an Arduino, and we are calculating the output temperature based on the curve that we obtained. As you can see, the Arduino gives a temperature between 23, 24 and 25. This is a fluctuation that is expected, and we are predicting the temperature accuracy of 2 degrees Celsius.
Next we are putting the blow dryer on our chip so that we can increase the temperature and make an accurate reading on the LCD screen. As you can see, you can see an increase in the reading of the temperature, which goes from 23 degrees Celsius to 30, now it's 31, and also simultaneously you can see that the PTAT reading shows 0.873, but the BGR reading is still constant, which is 0.634. It means that the BGR is constant as the temperature varies. Now the reading shows 33 degrees Celsius. So as we go on increasing the temperature of our chip, the temperature on the LCD screen also increases.
Thank you for watching the video. We would like to thank Professor Peter Kinget and our TA Vivek Mangal for their thorough guidance throughout the project.
If you have any further questions, please contact us. Thank you.